So this video is about the crystalline solids formed by various nonmetals. So we're going to look at three different types. We're going to look at covalent network solids, molecular solids, and clusters. So you'll see examples of these types as we go through, but here's some definitions that you can read. These are from your textbook. So first, we're going to look at some covalent network solids. These are some examples of some allotropes. Allotropes are one element, but you can assemble the atoms in different ways. They have different structures. So different structures of the same element are called allotropes. So carbon actually has several different allotropes. One of them we know is diamond. So this is a pretty cut diamond. They don't look like this when you mine them, but diamond is one of the allotropes of carbon. In this case, all of the carbon atoms have sp3 hybrid orbitals that they use for bonding according to valence bond theory, and they each form 4 bonds to other carbons. So that creates this sort of extended network-like structure. So we know some things about diamond. Diamond is very hard. It has a very high melting point, about 3,500 degrees Celsius. And those properties are due to the fact that all the carbon atoms are connected by these covalent bonds. So in order to break the diamond structure or melt it, you're going to have to break a significant number of these carbon-to-carbon covalent bonds, and it takes a lot of energy to do that. Some other things that we know about diamond is it's non-conductive, so it does not conduct electricity. It turns out that these electrons that are being shared between the carbon atoms are localized and can't move around the lattice in any way, so therefore they don't conduct electricity. So here's another one of the allotropes of carbon, and in fact this is the allotrope of carbon that is most stable under room temperature and pressure conditions. And this is familiar graphite, the stuff that makes up pencil leads. It's also used as a really good industrial lubricant, and we'll see why in a minute. So here's a picture of what graphite looks like. So you see it's kind of shiny, almost metallic, has a metallic luster to it. Well, it's in fact a two-dimensional covalent network. So again, it's one of those covalent network type of solids. But in this case, the carbon atoms have sp2 hybrid orbitals, so they make bonds to 3 other carbon atoms. Now what you don't see so well in this video is that each carbon atom has a unhybridized p orbital on it. So let's say here's a p orbital on one carbon atom, here's a p orbital on another. This neighboring carbon also has unhybridized p orbitals. So what's going on here is we're getting side-to-side overlap of these p orbitals, the electron that's in those p orbitals. So in fact this can happen all the way around these rings. So we say that the electrons that are in those p orbitals that form pi bonds are now delocalized along these rings. So you're actually sharing some more electrons with all the other carbon atoms delocalized along these rings. Now that's an important property because since the electrons aren't held tightly in one bond between two atoms, they're sort of free to roam around on this plane. It makes graphite a reasonable conductor of electricity. So it says they're conductive, right? So we can move the electrons around on the planes of these sheets. Now another interesting property of graphite is that even though we've got all these covalent bonds here in one sheet is not covalently bonded to the next sheet. In fact, they interact through those weaker dispersion interactions. But since there's so many of them, this material is held together relatively tightly, but the sheets can slip on top of each other, which is why graphite is a really good lubricant. But still, if you wanted to melt this, graphite has essentially the same melting point as diamond, about 3,500 degrees Celsius. So you have to put in a whopping amount of heat energy because you still have to break all of these networked covalent bonds between the carbon atoms in order to get the graphite to melt. So that's one reason it's a very good industrial lubricant, because you can put it in machines that generate large amounts of heat. You don't have to worry about your lubricant breaking down into goo because it doesn't melt until you get up to 3,500 degrees C. And yet it provides good friction reduction because these sheets can slide back and forth on top of each other. The last allotrope of carbon is something that we call a nanoparticle or a nanostructure. The name of this technical name for this molecule is Buckminster fullerene. It's named after an architect R. Buckminster Fuller, who used to design these geodesic dome-style structures. So this molecule, C60, is made up of 60 carbon atoms arranged in this sort of soccer ball shape. So it's a three-dimensional network of sp2 hybridized orbitals. So it looks kind of like if we had taken one of those sheets of graphite and folded it up into a ball. We might get something kind of like that, although we have these hexagons and pentagons, which is a little bit different. So fused 5 and 6 member rings. And you can make other size clusters, C70 and so forth. You can also shape these things into tubes, and so we can make carbon nanotubes, and these molecules have all sorts of interesting properties. In fact, nanotechnology is a big area of research today, looking at properties of these clusters of molecules. So now we're going to look at some allotropes of some different elements. So now we'll look at phosphorus. So phosphorus is a nonmetal, and there are two forms. This form is called white phosphorus. So it's a molecular solid, and what you have are 4 phosphorus atoms covalently bonded to each other in this little pyramid shape, a tetrahedron. This material is waxy and kind of soft, and if you expose this to air, it will react instantly with the oxygen in the air, pyrophoretically, we say, so it catches fire. It's quite impressive, and this stuff will continue to burn underwater, so it's really difficult to put this fire out. In fact, white phosphorus are used in certain types of munitions these days because of those properties. But interestingly, if you take the white phosphorus solid, these little tetrahedra, and you change the structure a little bit, so now you take these tetrahedra and you break a bond that was between them, and you create a new bond to another neighboring tetrahedra, so you make these long chains where these pyramids are kind of hooked together, well then you've made red phosphorus. So red phosphorus is very different. It's kind of chalky, powdery, and it's stable in air. You can let this allotrope of phosphorus sit in oxygen without having to worry about it bursting into flames. Here's some other examples of some molecular solids. So boron forms B12 clusters, this really cool 12-sided shape that we call an icosahedra. So boron has a cool shape. Here's sulfur. Sulfur, in fact, has more allotropes than any other element. Most commonly, sulfur exists in this sort of ring of single-bonded sulfur atoms, but you can get other structures as well. Then to make the solid sulfur, these rings would interact with each other via dispersion interactions to make a soft, low melting point solid. Then we turn to molecular solids. So molecular solids are made from compounds. So here's an example of carbon dioxide right here. So these are made up of carbon atoms and oxygen atoms, and they're held together by those weak dispersive interactions. But you get this stuff cold enough and you can lock this together into a crystal lattice. So there are intramolecular forces between the carbon and the oxygens, but intermolecular forces hold this together in a crystal lattice. Here's another example of a molecular solid made of molecules, and this is ice. So here you see water molecules, the oxygens and the hydrogens are covalently bonded. And then there's a hydrogen bond, which is not really a chemical bond, but an intermolecular force, connecting a hydrogen to an oxygen. And in fact, the water molecules deep inside this lattice will make 4 hydrogen bonds. So notice some interesting things about this lattice. It's got a lot of empty space in it. See right here, this empty space right here? And they're all over the place. So when you melt ice, these molecules will break some of these hydrogen bonds, and these water molecules can tip inside this empty space. And you create a structure that's more dense. So that's why ice is less dense than water, because it has to maintain this open structure in the lattice so that all the water molecules can hydrogen bond to 4 neighbors. Another interesting thing about this structure, it has this sort of 6-sidedness. You can sort of see the hexagon shape right here. It's not perfect. But you'll notice that when you look at snowflakes, they sort of have an inherent 6ness about them, and that comes about due to the underlying molecular structure. So that's pretty cool. Macroscopic properties determined by the microscopic structure. So in the next video, we will look at ceramics.